Well, hello. We're recording ap2, Chapter 9, Part 2. I still haven't got the microphone yet, so get ready for some tapping. We're going to be starting on page 274, looking at section 9.3. Density and pressure. So the first thing to talk about is density. We are going to use the Greek letter rho to represent density. Rho is just like a P with a curly tail. Start here, roll around like a P, and then continue on making a tail. Start here, head around like you're making a P, continue down, make a nice little tail. The Greek letter rho. And that is the Greek letter rho, if you care about spelling. Anyways, density is a measure of the amount of stuff that makes up an object. Density is defined as mass per volume. It has the units, kilograms per the unit for volume, which would be the meter cubed. So density is mass per volume and has the units, kilograms per meter cubed. Another term you actually hear from time to time is called specific gravity. This isn't something we're going to hear very often, but the term specific gravity is just a term that describes the density of an object compared to the density of water. So the density of an object, it is the ratio of a density of an object to the density of water at 4 degrees C. The density of water, hold on, let me make some room. The density of water is 1,000 kilograms per meter cubed. So you have some object, its specific gravity would be the ratio of that object to the ratio of water. So if an object was said to have a density, a specific gravity rather, of 2, then you know that its density would be 2 times 10 to the 3 kilograms per meters cubed. All right. If you look back at your textbook, you will see table 9.3. Table 9.3 lists the densities of some very common substances, ice, aluminum, iron, etc. And there you have that. Hopefully that answers all our questions about density. Moving on to the next subject, we want to talk about pressure. Oops, wrong thing. Specific gravity, now we want to talk about pressure. So pressure we're going to define as, so let's use capital P, that's a capital P. Pressure we are going to define as force per area. We're going to define pressure as force per area. We're going to be talking in a few minutes about the pressure we experience while inside a fluid, while submerged in a fluid, remembering fluid is liquid or gas. But in more general terms, pressure is just the force per area. If you push on the wall, you are exerting some force on that wall will experience some pressure. The pressure the wall will experience will be the force you are pushing on the wall with, divided by the contact area. If you're pushing on the wall with your hand, the contact area is not the area of the entire wall. If you're applying that force with your hand, then the contact area would be the area of your hand. What a horrible hand. I am sorry you're gimped. But the area would be this area. Man, is that an ugly hand? I am so sorry that you have such an ugly hand. I won't judge you. But that would be the area. Okay? Moving on before we start feeling bad about ourselves. The air in the room you're sitting in right now, assuming you're sitting in a room, is exerting a pressure on the wall as well. The pressure on the wall exerted by the air in the room would be the force the air exerts on the wall. So all these little air particles, all these little air molecules banging into the wall, exerting force. All of that force divided by the area of contact. Well, the area of contact in that example would be the entire surface of the wall. Air is bouncing into the entire wall, so it would be the force the air applies divided by the entire area. So the area is going to be the part you got to get used to figuring out, and that's the easiest way to visualize it is the area of contact. So another silly example. Let's just say that that is the ground. And let's just say that this is your shoe. And here's your leg. Okay? Man, again, sorry about your body there, guys, but it is what it is. I won't judge. The force that the ground exerts on your foot, so what pressure would your foot experience when you put your foot on the ground? The force the ground is going to exert on your foot, that force is just going to be the reaction force of your weight, right? Gravity pulls you down with some force. The ground is going to push back up with that same force. So the ground will push up with a force equal to your weight. And the area is going to be the entire surface area of the ground. Nope. It is going to be the area of the bottom of your foot. It is your shoe that is experiencing the force. Your foot is experiencing the force. The ground is exerting that force on you through the entire surface area of the bottom surface of your foot, of your shoe here in this case. All right, let's do a sillier example. This is going to be, I like this one better. So instead of standing on the ground, let's stand on a bunch of nails. I know, right? There you go, there's a bunch of nails. Let's stand on those. Well, those nails are going to exert a force on your foot in that direction, and that force, just like the previous example, is going to be mg. It is going to be the reaction force to your weight. Gravity pulls you down, nails are pushing back up. This time, the area is not going to be the area of the entire bottom of your shoe. It is going to be the area of all of those little nail heads. So the area is going to be that one, plus that one, plus that one, plus that one, plus that one, etc. Okay? All of those add together, give you the total area. The pressure that you would feel on your foot would be force divided by that area. Well, we've gone this far now, and I'm sure you don't need to see this, but, you know, what the heck. Let's just do another even sillier example. Let's stand on one nail. Well, the force that nail exerts on your foot is just like before. It's just going to be the reaction force to your weight. So it's going to be an upward force equal to your weight. The area this time is just going to be the area of one nail head. So the pressure is going to be, again, force per area. This time the area is tiny. So the ground exerted a force on the entire bottom of your foot, so that was a large area, so that force was diminished by a large number, so a small pressure. You stood on a bed of nails, well, the area got smaller, so the amount of force was distributed over less total area, so there's going to be a larger pressure. Most likely, unless you jumped off a roof onto a bed of nails, your shoe would survive that. You wouldn't get punctured. Now you go to step on a single nail, and well, you're going to feel that one through your shoe. The area is really small, so that amount of force per area is going to be very large, so you'll get punctured. I don't know if any of you remember what stiletto heels are. Some of you women might know what they are, but imagine a heel that had imagine high heels that have a very, very pointy heel. There was a time period in recent history where those were actually not allowed on airplanes for fear that the tiny pointy heel could puncture the floor. Well, as it turns out, there's lots of holes in airplanes anyway. That's why they have to constantly pump air in to keep pressure up. So that wouldn't have actually mattered anyway. And besides, the floor doesn't escape to the outside of the cabin anyway. So that was a bit silly, but the airlines actually did that. Okay, so moving on. Moving on, and units. Force per area, well, the units would be the units of force, and the units of area would be a Newton per meter squared. We're going to give a special name to a Newton per meter squared, and we're going to call that a Pascal. And we will use PA for short. So the units of pressure will be the Pascal, PA. All right, another thing you're going to hear, another unit you will hear is the unit of atmospheric pressure, or 1 atmosphere. 1 atmospheric pressure is equal to 1.0001, so in other words, 1 times 10 to the 5 pascals. most of the time we're going to call it 1. Depending on your precision, you might need to extend out all the zeros. Maybe I went to too many zeros. I'm doing this off the top of my head, so I might have got the number of zeros wrong. Now that I'm thinking about it, it might actually be 1.01 times 10 to the 5 pascals. My memory's getting better about that one, so let's go with that. Anyways, really close to 1 times 10 to the 5 pascals. Another number you might be familiar with, pressure, is going to be 14 pounds per square inch. That is going to be an atmospheric pressure. On every single square inch of your body is 14 pounds. On every square inch of your body is 14 pounds. That is the weight of a large cat on every square inch of your body. I find that to be fascinating, to think about the fact that we walk around on the surface of the earth with that kind of force applied to every square inch of our body, and we don't even notice it. That's really cool. All right. Next thing to talk about is pressure in a fluid as a function of depth. By the way, I'm skipping the problems. We're going to work out the problems live in class. So live via the stream. So we'll do the problems later. I'm just getting that information out there. So the next thing to talk about is going to be pressure as a function of depth while in a fluid. In other words, we want to talk about, hey, where did I get that bed of nails idea? We want to talk about the variation of pressure with depth, page 277, section 9.4. So, let's imagine we're in a fluid, and remember, a fluid could be a liquid or a gas, so right now you are in a fluid called air. I'm going to use the analogy of going underneath water because that's something that we more tend to think about, and I don't know, I just feel like doing it with water. You've noticed when you jump into a swimming pool or into a lake or something, the deeper you dive down, the more your eardrums start to hurt, and quite often you find the pain in your eardrums starts to bother you before you run out of breath going swimming down. Well, that's an experience you've had that shows you that the amount of pressure as you go deeper and deeper in a fluid increases. The way to think about that is the pressure that you feel as a result of being in a fluid is directly related to the weight of the fluid above you. So imagine sitting in wherever you're sitting right now, you're in air, and that air is exerting pressure on you. That air you can think of as a column of air that is the exact shape of your body, and it extends all the way up from you to the edge of the atmosphere. That column of air has some mass, and as such has some gravitational force on it, so has some weight. The pressure you feel is related to the weight of the fluid up upon you. Well, if you were to leave the ground and go to the top of Mount Everest, there would be a much smaller volume of air sitting on top of you. The amount of air above you would be a lot less. So the pressure you would feel would be a lot less. The weight of the fluid would be a lot less. So you've experienced this. The deeper you go in a fluid, the more the pressure. Let's look at this mathematically. So here's some container, and we're going to put some fluid in it, and we're going to take some square chunk of stuff. Let's just use a cube so the math's easy, but it works with any area. So there's some chunk of stuff, and we'll just say that that chunk of stuff has a side that is length h. And well, let's start looking at this. That pressure from that fluid is going to start exerting forces which result in pressure on all the sides. A fluid will exert a force perpendicular to a surface. If you're submerged in water or submerged in air, that fluid will exert forces on you perpendicular, always. So, if you think about it, the force being exerted right there on that side is going to be at some depth. The force exerted you on that side is at the exact same depth, so it would be the same force, so ultimately the same pressure. One's to the left, one's to the right, that would cancel out and give you a net force of 0, so those cancel. So that cancels. Same argument if you went to that depth on that side and that side, same argument. Same depth, same amount of pressure, same force, opposite directions, cancel. If you had a force exerted on the front side and then on the back side at this depth, they'd cancel. A force on the front side there and a force on the back side at that same depth would cancel. The only place we're not going to get forces canceling out are going to be force in that direction and the force on that surface. Those are not at the same depth, so those would not be different. Okay? The only other force we're going to see is going to be the force of gravity. So let's just call this one force 1, and we'll call that one force 2. Okay? So give ourselves some room here. Free body diagram, we would have force 2 is that way, force 1 is that way, and we can't forget weight. Gravity's pulling down that way. So on our object, we have force 1 down, force 2 up, and gravity pulling us down. So let's look at the net force. Oh boy, we haven't done this in a while. What's the net force? Well, the net force in all the directions but the vertical direction will be 0. In the vertical direction, the net force, oh, I can't go on, I'm sorry. That bugged me. The net force would be force 2 minus force 1 minus mg, and all that's going to add to 0. Why am I saying that's going to add to 0? Because had I said it earlier, you'd have remembered, but I didn't say it earlier. We're talking about an object that's just suspended there. It's not going anywhere. It's just sitting there and feeling forces. We're talking about equilibrium here. We're not actually moving or accelerating. So all the net forces add up to 0 because we're not accelerating the object. All right? So, force 2. Well, if you remember, pressure equals force per area. So force must equal pressure times area. So the force of F2, so the force from F2 would be pressure 2 times area. Now we're pretending this is a cube for now, so the areas are going to be the area of the surface, the side that we're talking about. So this is the area of the bottom of the cube, so it's A. Minus force 1, which would be pressure 1 times area. It's the same, it's a cube, so the area is the same. Minus gravity, right? Which would be mg. And all that has to add up to 0. All right? Now, what is the mass that we're talking about? Well, I don't know the mass of that object, but I do know that mass is going to be equal to density times volume. Remember, density was mass per volume. So mass is density times volume, right? And what's volume? Well, the volume is going to be the area, the surface area of that object, the area of that side times h, right? If the side has an area A and a height h, then the surface and the volume is going to be A times h, right? The side of an area, the size of an area times that height gives you the entire volume. So our mass could be written rho A times h. The density of the material times the area of a side times the height. Agreed? So P2 area minus P1 area minus rho area h, and we got to remember our g. Remember, force, gravity. So mass is rho ah, so mg would be rho ah times our g. Got it? Make sense? And that has to add up to 0. Well, what can we do with this mass? Well, let's see. Area has in every term, so we can get rid of that. We can say that P2 is going to be equal to P1 plus rho GH. I reversed G and H. It just doesn't look right at having HG. Cool? So the pressure down here is going to be equal to the pressure here plus a term to account for the fact that the pressure is bigger down lower. So you have some initial pressure and some final pressure, and they're different by a term. And you'll have your final pressure at the bottom is going to be the initial pressure at the top plus some term to account for the fact that we're deeper. A more generic way to write this equation would simply be the pressure at anywhere you care about will be some initial pressure plus a term to account for the fact that you are now deeper, at depth h, into the fluid. It's going to depend, of course, partially on the density of the fluid. A very very high density fluid will exert more pressure on you as you go under than a low density fluid. We are several miles below the surface of the atmosphere, and we only feel 14 pounds per square inch. If you were to go a mile below the surface of the ocean, you'd be squished down to the size of, well, something really, really, really tiny. Okay? So let's see what else we need to do. No, I think we got it, actually. The only thing left to do on this section is to solve some of the problems. We'll solve the problems in class, so I'm going to end here. Thanks.